All right, everyone, get ready because today we're going deep on entropy.
Ooh, entropy.
But don't worry, we're not going to get lost in textbook definitions or anything.
Yeah.
We're going to explore entropy in kind of a new way through a game. It's called the Ising Conway Entropy Game.
Okay.
ICEG for short.
Catchy.
It's kind of like a zero-player game, which I know sounds a little strange.
It does.
But basically it means you just set the rules and then you watch what happens.
Yeah, it's like a simulation.
Exactly, like a simulation. So it's a really cool way to kind of visualize how systems naturally tend toward disorder.
Yeah, even when we're not actively messing things up. Have you ever noticed how even if you organize your sock drawer perfectly, it always ends up a jumbled mess?
It's inevitable.
It really is.
So for this deep dive, we're using a recent research paper as our guide. It's called Understanding Entropy Production via a Thermal Zero-Player Game.
Okay.
And it was published on March 7th, 2025. So very recent.
Very cool.
So we're dealing with some cutting-edge stuff here.
And what's really cool is that this game helps us understand a pretty big concept in physics, the second law of thermodynamics. And that basically says that entropy, or disorder, always increases over time.
Okay, so how does IC actually work?
So imagine a line of, let's say, light switches
Okay.
that are either on or off, and that's our game board. It's called a one-dimensional lattice.
Okay.
We start with a few of those switches on at one end, and then we let the game run based on these rules that are kind of like mimicking how particles behave in a system.
So are we basically watching how these on switches kind of spread out and represent increasing disorder?
You got it. It's yeah, exactly. Like watching your neatly folded laundry slowly over time just becoming this big jumbled pile.
Okay, I'm starting to get it, I think.
Good.
But there's got to be more to it, right?
Oh, yeah, absolutely. So the way those switches change from on to off, or vice versa, is based on something called spin-flip dynamics.
Spin-flip dynamics. All right.
Which sounds complicated.
It does.
But basically, just think of them as algorithms that simulate how particles would move at different temperatures.
Oh, so temperature is a factor in this game.
Temperature is a huge factor. Yeah.
Okay, that's where that thermal part of the research paper comes in.
Exactly. Yeah, temperature basically represents how much energy those particles have. So higher temperature means things are going to be more chaotic and spread out faster.
So adding heat to a system makes things more disordered faster.
Exactly. If you think about how ice melts, it melts way faster on a hot day than on a cold day.
Right, yeah.
So it's all about the rate of change.
Okay.
And that's actually one of the key things they found in the paper. They found that, just like you'd expect, the higher temperatures in the game lead to faster entropy increases.
Okay, well, that makes sense, intuitively.
Yeah.
But the paper also looked at entropy production.
Right.
What is that exactly?
So entropy production, you can think of it as a measure of how much faster entropy increases compared to the lowest temperature they tested in the game.
So it's comparing the rate of melting on a really hot day versus a barely above freezing day.
Yes, precisely.
Okay.
And here's where things get really, really interesting. What they found was that there's a limit to how fast entropy can increase.
Wait, really?
Even with unlimited heat.
Whoa, so even chaos has a speed limit.
It seems that way.
That's wild. That was not what I was expecting at all.
It's pretty surprising.
So even if you pump tons of energy into a system, there's still a cap on how quickly disorder can take over.
Yeah, that's what this research seems to suggest.
This is blowing my mind.
It's pretty cool, right?
All right, so to recap, we have this game, IC, that models how systems tend towards disorder.
Yeah.
And we've learned that higher temperatures speed up this process. But even with a ton of energy, there's a limit to how fast disorder can increase.
Like a cosmic speed limit on chaos itself.
Right, exactly. And it's all thanks to these spin-flip dynamics,
right,
which add that element of temperature into the game.
Right. Those are those algorithms that determine how those occupied cells on the lattice on our game board can change.
Right. Okay.
The paper actually focuses on two different types of these dynamics, Metropolis and Glauber Dynamics.
Okay.
And they actually found some pretty interesting differences in how they influence those entropy increases.
Really? Like what?
So, for example, they found that with the Glauber dynamics, the difference in how much entropy increased between low and high temperatures was way more pronounced than it was with the Metropolis dynamics.
So does that mean one is better than the other for studying entropy?
Not necessarily. They're both really valuable tools. It's more about using the right tool for the job, like a chef choosing the right knife for a specific task.
Right, okay. So it's about understanding the subtleties and when to use each one.
Exactly.
Okay. But I'm curious, what does any of this have to do with us outside of this game?
Right.
Like in the real world? What are the implications of this entropy production limit?
Yeah, that's the big question, right?
Yeah.
Well, think about something like climate change.
Okay.
One of the huge concerns is how quickly the Earth's climate is changing
Right.
because of all those increased greenhouse gases.
Yeah. Yeah.
So if there is some kind of natural limit to how fast entropy can increase, it could actually impact the pace of those climate shifts.
Whoa. So you're saying there might be a natural break on how fast the climate can change,
And it's possible.
even with all the greenhouse gases.
It's a possibility.
Wow.
And, of course, climate change is incredibly complex.
Oh, yeah, for sure.
There's tons of factors.
Definitely.
It's not like a direct comparison to this simple game,
Right.
but it does offer a new way of looking at those kinds of complex systems.
Yeah. No, that's a really interesting point.
Yeah.
It makes you wonder, like, if there might be similar limits in other areas, too.
Yeah.
Like, what about biological evolution?
Ooh, that's a good one.
We see life constantly evolving towards greater complexity.
Right.
But, I mean, is there a limit to how fast that can actually happen,
Yeah,
even with all the pressure of natural selection?
that's a great question. And it's one that evolutionary biologists are, still trying to figure out.
Yeah.
It's like, is there a speed limit on how quickly a species can adapt
Right.
to a changing environment?
Yeah.
We don't know.
And what about technology?
Ooh,
Like, we've seen incredible advances
for sure.
in computing power and innovation,
Yeah.
but could we hit some fundamental limit to how fast technology can progress?
It's certainly a question worth considering, right?
Yeah.
I mean, this concept of an entropy production limit
Right.
suggests that even in systems that seem to be just accelerating, like rapidly,
Yeah.
there might be some inherent constraints that we don't even fully understand yet.
So this seemingly simple game
Yeah,
is opening up some pretty profound questions
it is.
about the nature of change and the limits of progress.
Absolutely. And that's what makes science so cool, right?
Yeah.
It often starts with just the simple model or observation,
Right.
and it leads to these unexpected and profound insights
Yeah,
that really challenge how we understand the world.
totally, totally.
Yeah.
Okay, so we've kind of explored the broader implications of this entropy production limit in different fields.
Yeah.
But let's go back to the icy egg for a sec.
Okay.
The paper mentions these two spin flip dynamics that are used in the game, Metropolis and Glauber.
Right.
Can you just break those down a bit more for us?
Sure. So remember those light switches we talked about?
Yeah.
The spin flip dynamics, they're basically the rules
Okay.
that decide when a switch can flip from on to off or vice versa.
Okay.
So Metropolis and Glauber are like two different rule books,
Gotcha.
each mimicking how particles would move at different temperatures.
So they're kind of like different versions of the same game.
Exactly.
Yeah.
And what they found is that these different rule books can actually lead to slightly different outcomes in how quickly entropy increases in the game,
Yeah.
for instance. With the Glauber dynamics, you see a much bigger difference in entropy increase as the temperature goes up compared to the Metropolis dynamics.
So the Glauber dynamics are more sensitive to those temperature changes.
Yeah, it's possible. It might make it a better fit for looking at systems where the entropy changes really fast with temperature.
Yeah.
Like it just shows that even in a simple model like the icy egg, those little tweaks to the rules can really change things.
Yeah, that makes sense.
So pretty wild.
So even with something as fundamental as entropy,
Right.
there's still so much to learn.
Oh, absolutely.
And there are nuances and complexities to, like, figure out.
Definitely. That's what keeps this field so exciting,
Yeah.
There's always more to discover.
It's amazing how we started talking about something as basic as a messy sock drawer
I know, right?
and ended up discussing, like, the limits of chaos and the future of technology.
It's kind of mind-blowing.
Yeah.
That's the beauty of science, though. It connects those everyday things to these huge ideas about how the universe works.
My mind is officially blown.
Good. That's what we like to hear.
I feel like I have a much better understanding of entropy now
Awesome.
and, like, its role in the world.
That's what we aim for, right? To make these
Yeah.
complicated topics accessible
Totally.
and hopefully get people thinking.
Speaking of thinking,
Yeah.
what's, like, the main thing you want listeners to take away from all of this?
I think the most important thing to remember is that even chaos has its limits.
Okay.
Entropy might be this force that pushes everything towards disorder.
Yeah.
But this research suggests that there might be some built-in constraints
Okay.
on how fast that process can actually happen.
So it's not just like a straight shot to complete randomness?
Not necessarily. There might be a more, I don't know, like a back and forth
Yeah,
between order and disorder,
right.
with some limits and boundaries that we're just starting to understand.
Kind of comforting, in a way. To think that even with increasing entropy, there might still be some underlying order or structure there.
Exactly. And that's why it's so important to keep exploring these ideas,
Yeah.
to push the boundaries of our knowledge.
Keep asking those questions.
Exactly.
Well said. I think we've given everyone a lot to think about today.
For sure.
Any last words of wisdom before we wrap up?
Just remember to keep an eye on your sock drawer.
Uh-huh.
Entropy is always lurking.
It's true. It's true.
But seriously, I encourage everyone to stay curious about the world.
Yeah.
You never know what amazing things you'll find.
I love that. Well, thank you so much for joining us on this deep dive into the world of entropy.
Thanks for having me.
Until next time, keep those minds engaged.
And those explorations going.